Hello student. So let us start our discussion. In previous session we have discussed that what is address sequencing and which are the some terminology of address sequencing. So there we have tried to discuss what is routine, what is mapping, and then which are the expected capabilities of any sequencer. So in this video we will try to understand the individual elements of this address sequencing circuit. So let us start to understand individual element one by one. Okay, so we will start with the status bit. So what is meaning of this? Meaning of this is to focus on the various flag of the we can say CPU, like interrupt enable flag is there, then we can say carry flag, zero flag, sign flag, then overflow flag. Okay, then input flag is there, then output flag is there. Okay, so we are having uh, lots of means 8 flags are there total in computer. So using this bit, if we want to select a particular address, then these bits will be given as an input to the branch logic. Okay, so in branch logic this status bit will be given, and based on the certain values of the status bit specific address will be selected. So if it is 1, then what will happen, and if it is 0, then what will happen. So this will be specified using special bit. Now let us discuss what is branch logic. So branch logic will get status bit input. So let's say we are having total 8 bits. So if we want to check the status of individual bit, then we can have total 8 we have to use 3-bit combination. Why? Because 2 raised to 3 is for 2 raised to 3 equals to 8. So like 0 0 0 0 1 0 0 1 0 1 0 0 1 1, then 1 0 0 1 0 1 1 1 0 1 1 1. So let us assume that this individual bit represent the individual combination represent the individual flag. Let's say, for assume that first one is for interrupt enable, next is for carry, next is for zero, next is for sign, next is for overflow, next is for input, next is for output, and next last one is for, let's say, R. So if a particular bit means, let's say we want to check the condition of carry flag. Okay, so we will give 0 0 1 as input to branch logic, so it will check the carry flag. If value of carry flag is 1, then a particular address will be selected. Okay, using branch means whatever branch is there, that address will be selected. But if this flag is not set, means condition is false, then it should accept the default input from the incrementer. Okay, so this is how we can implement the conditional branch, where we will check the various condition bit. Okay, and if a particular value of a particular bit is true, then it will select a particular branch address. Otherwise it will get the input from the incrementer. And next doubt will be how we can implement the unconditional branch. So let's say for unconditional branch we can implement a specific condition, like let's say if there is a 1 1 into the particular condition bit, that means it will directly load the branch address from the control memory via control address register. At that time it will not look for any other source. So this is how we can implement a branch, conditional branch and unconditional branch. Okay, so for that we will use status bit. Where we will use various bit combination to check the individual flag, and using that value of flag, whether it is 0 or 1, based on condition, we will transfer the branch address from micro instruction to the multiplexer to the control address register, and then we will retrieve the new instruction. While in case of unconditional branch, by default it will be, let's say we will keep 1 1, so it will not go with any condition check, but it will directly go to the next line, or it will go with the incrementer. So this is how unconditional branch can be implemented. Okay, so till now we have discussed what is status bit, then what is conditional branch, what is unconditional branch. Means we have tried to discuss various input of this multiplexer, means how branch logic, how branch address can be used, then incrementer can be used. Now we will try to focus on what is mapping. So let us assume that control unit is having 128 different memory location. Okay, so 2 raised to 5, 32, 2 raised to 6, 64, 2 raised to 7, 128. So 7 bit will be required to specify any address into the control memory. Okay, so now how it will be done? So what we will do, how it is implemented, these 128 location are divided into two parts: 64 64, 0 to 63, and 64 to 127. So this portion we will keep for subroutines. Subroutine like what subroutine for fetch, then decode, then subroutine for, you can say, indirect addressing mode. Clear? And then subroutine for we can say interrupt. Yes, so we are having total 64 locations starting from 0 to 63. Okay, so if we start with the first location, then it will be 1 0 0 0 0 0 0 and 0. Okay, last location for 63, it will be 0 1 1 1 1 1 1. Okay, so this portion will be used for instruction. Clear? Now we know that in instruction register there are 16 bit, so 12 bit will be used for, let's say, address, and 4 bit will be used for opcode. So simple logic mapping, simple logic of mapping, how it can be done. Let's assume that this is the instruction, which is having opcode 0011, and then this is 12 bit address. Okay, so this will be directly converted into control memory address in this way. First bit will be always 0, this 4 bit will be as it is, and remaining 2 bit. Okay, now this is really interesting. So what is meaning of this? If we go to this memory location, then there we will find the routine, means the steps which we have specified in memory reference instruction on this location. Okay, now we have seen that in add instruction, after getting the effective address of operand, there were two steps. One was for getting operand from the memory, and second was for performing the operation into accumulator, and then again storing result into accumulator, right? So where these steps will be stored, so those steps will be stored like this. So this will be step number one. Okay, next step, it will be 0 0 1 1. On this location, here it will be step 1, here it will be step 2, then 0 0 0 1 1 1 0. There will be step 3, 0 0 0 1 1 1 1. There will be step 4. So whatever steps of individual instructions are there, okay, all those steps will be stored in this way. Okay, so if we use let's say for memory location, for control memory location for one instruction, okay, then we can have a 16 instruction. Why? Because 16 into 4 equals to 64. So we are having only 64 locations, 0 to 63. So on this 64 location we can store various instruction. Okay, but here each instruction will be stored in form of group of steps. Okay, so here group of 4 steps is specified. So this is how mapping can be done. So while you are retrieving any operand, so it won't be you are performing any instruction execution, so it won't be like that computer will do it automatically. Okay, so it will go to this location, then mapping process will be done. So we will have a location of control memory, and then on that location the execution will be step by step. Once the instruction is over, it will automatically go to the routine of fetch and decode. Now that routine will be stored into uh, remaining half portion of memory, okay, which is 1 all 0 to 1 all 1. Okay, here in first portion, step means instruction, size of instruction was fixed, it was only 4 steps. So any instruction must be completed into the 4 step, 1 2 3 4. While here the size of routine, it is not fixed. If we are having, let's say, 256 location, okay, and let's say we are having 6-bit address, okay, 6-bit opcode, so 2 raised to 6 64. Okay, and so instead of 6-bit, let's take we are using 5-bit for opcode, right? So 5-bit will be used to specify any operation. So if we are having 256 location, then we will require 8-bit. So this entire memory address range will be divided into 2 parts. So all 0 1 all 0. So sorry, it will be 0 all 1. So 0 to 127, and next will be 1 all 0 to 1. So 128 to 256. Now here, how many bit we are using for opcode? 5. Okay, so let's say this is address and these 5 bits are opcode. So in that case, what will happen? 0 and this 5 bit will be used as it is. Okay, clear? And remaining 2 bit will be used to specify the instruction. Clear? Let's say if we are having let's say 16 operation. Okay, so we will require only 4 bit. So 0 and 4 bit will be here and 4 bit will be used here. So any instruction can have a 16 steps. In 16 steps instruction will be over. Okay, so this is how mapping will be done. Clear? Yes. So till now we have discussed what is the first input, that is branch, then incrementer, then mapping logic. Now let us discuss what is subroutine register. So what is need of subroutine? So subroutine will consist a code or set of micro instruction that will be common to all the instruction. For example, here we are having subroutine for fetch and decode. So fetch and decode will be part of all the instruction. So if we do not create subroutine for fetch and decode, then what will happen? Let's say if we are having 16 instruction, okay, then for fetch and decode required for fetch and decode we require 3 memory location. Then out of 128, 48 location will be occupied by fetch and decode routine only. Why? Because fetch and decode code only. So we can say the 50% of memory will be occupied by duplicate code. So this routine will help us to save the space and we can accommodate more number of instruction. So the second part of this memory, control memory, will usually store this kind of routine which will be helpful to CPU to perform the other operation or the code which is common to every instruction. For example, indirect addressing mode. So it is the, if we do not have a subroutine, then there will be separate instruction for we can say direct addressing and separate another instruction for indirect addressing mode. Okay, so there will be one AND instruction using direct and same AND instruction using indirect, so which will result into duplication of code. So this routine help us to save the control memory space, so more number of instruction can be accommodated. So whenever any subroutine is implemented, there should be a functionality where we can store the return address. So that task is done by SBR, subroutine register. So at the end of the subroutine, there will be the there will be certain condition bit. So if those condition bit are given it as input to branch logic, then those condition will make multiplexer to select address, return address from the subroutine register. So this is how subroutine portion will work. Clear? So there are the various portion. We will combine all these condition and then we can implement the sequencer. So let me quickly revise. So this is the multiplexer, this is control address register, this is control memory, and here we will get the micro operation. So if we start with the basic, then the first was the conditional branch, where we have considered the various flags like carry, input, output flag, then overflow flag, sign flag, zero flag. So those status bit will be given, and accordingly accordingly particular branch will be selected from the we can say micro operation, control word or control memory. So and that how we can implement the conditional branch. If condition is false, then by default input will be taken from the incrementer. Next, we have seen the unconditional branch. So if we keep the value of certain bit to, let's say, 1 1, then by default it will go to the next location rather than going to a specific branch or specific location. Or we can directly provide the address from control memory, and that address will be directly selected. Then we have seen the mapping logic. So this is how whenever an instruction will start, so initially the mapping process will be done, means conversion of opcode into the address of control memory, and then it will be given as input to multiplexer. And then at last we have discussed subroutine register. So whenever we will implement any routine, there should be a mechanism using which we can return to normal execution. So that task will be implemented using subroutine register. Subroutine register holds the return address. Okay, so once the routine is over, multiplexer will select, it will not select any other source, but it will select the return address from the subroutine register, and then it will resume the normal execution. So this was all about address sequencing. In next video we will try to learn what is micro instruction format, and how we can understand the micro program. So that's it for this tutorial. Thank you.